Okay, so what it is and how it works, how things are going to dependent with respect to deformation mechanism, all those things we are going to learn today. Another 1 minute I am giving. Hope everybody will can join between that. So let's start. So look at the picture and then you just listen my discussion and try to correlate with the picture presented in the slide. So suppose when it is extremely difficult to induce sleep over plane, then the tuning mechanism generally is to operate it. So if you take a scenario, if basal plane, if you look at the HCP crystal, basal plane is parallel to the tensile axis, then it will be very much, very difficult or extremely difficult to induce sleep over a particular plane. And then what will happen? That planes may kink under compression. If you look at the picture, these things is shown, and that actually leads to a localized region near the buccal region. So if you look at the first part of the picture, then you can understand that the certain kink formation under compression, and these localized regions are very near to the buccal region. So if you want to tell in different words that kink is produced when sleep on a single plane is not sufficient in order to maintain homogeneous deformation. So homogeneous deformation, maintaining the homogeneous deformation, you need to have a sleep mechanism operation. But kink is produced when that sleep is not going to happen, and then you can see certain kink formation under compression. And if you correlate with the lecture uh, with my discussion, then you can easily understand. Then the grain sharply kink around the rotation axis is also shown in the figure and enables shortening of the grain is going to occur. So if you look at the pictorial representation of that phenomena, then you can see there is a rotation axis and sleep plane and kink band is formed. And if you look at the non-deformed crystal and the sleep direction, and then you can understand. So kinking generally present in the face-centered cubic metals deformed in the tension. And when it will happen, when slip lines curl off in the kink region, and then again they become straight as represented in the pictorial or schematic figure of the slide. And what it indicates, if you look at that, it actually indicates kinking indicates that kinking is highly localized phenomenon. Kinking process is very localized phenomenon. It's not going to spread globally across the specimen. Okay. And so when we will read about or discuss about the Watt hardening, then we will understand how the introduction of kink bands induces faster Watt hardening process. Those things we are going to understand when we will discuss those things, those Watt hardening or hardening phenomena. So in case of kinking, if you look at the picture of this slide, part of crystal lattice is slowly transformed under the action of stress into another crystal orientation. So there is a variation in crystal orientation. And what will happen? That variation is due to the slow transformation by the action of stress, and that orientation variation of the crystal is going to happen if you are looking at on the perspective of kinking process. But neither the new orientation or nor the plane of kinking bear any spatial relation to old lattice. So kinking, if you look at, there is no spatial relationship with that. Okay. But interestingly, if you look at the picture, that twinning may look similar to the kinking. However, there exists a unique relationship between old and new or twinned crystallographic plane. So in order to introduce the idea of twinning, first you have to understand what is the difference between slip, kinking, and twinning. So in this slide, we are going to understand that. Then we'll introduce the actual twinning phenomena, so that our concept should be very clear with respect to perfect specimen, that is non-deformed specimen, slip, and deformation twinning, and then deformation kink and band. So if you look at kinking thing, due to the slip process, it is a common secondary mode of plastic deformation. It's a very well-known secondary mode of the plastic deformation in a single crystal. With at least one plane should have easy slip option. Okay, but can be found in the crystal of any symmetry class. It also may be found in the any symmetry class. So you can go for quartz or olivine or kyanite, all kinds of solutions. We are not going to talk about that. So it is a second most important takeaway point is it is the common secondary mode of plastic deformation in case of single crystal, which is having at least or one plane of easy slip. So like other plastic mechanism, kinking does not involve an increase in crystal volume. Like other plastic deformation mechanism, what we know, the volume of the specimen are not going to change. So although kinking is primarily thought to accommodate shortening of crystal parallel to maximum compressive stress, it may also take place in crystal stress in tension. So what does mean that? That when you are thinking that how kinking going to create a scenario where it accommodates shortening or it actually shortening of crystal parallel to the maximum compressive states. So kinking is important for considering in plastic rock deformation. If you take like that, and it is an accommodation mechanism for larger processes like twinning and slip. So kinking actually is an accommodation mechanism for along with the twinning and slip. Twinning we do not know, but slip we do know. So crystals unfavorably oriented for slip are free by kinking, which rotates the lattice around a or along the rotation axis, what is shown in the previous figure, and which actually subsequently help for occurring further plastic deformation. So multiple king band may form, that is a possibility is there. Now we are going to understand what is twinning. So if you want to know, hello?
Sir, I have a little misconfusion. Can you please again elaborate? We have said that uh, kink is a localized deformation, which means we can't find it global. I mean, overall entire lattice. But you have also said that there can be a chance of more kings.
The chance of
More kings, if I'm not wrong.
multiple kings.
Yes, sir.
So is it what I told is very clearly, very clear and very transparent. First, your question is like that. That I told that kinking is a localized deformation, and on the contrary, also I am telling that it is multiple king may form. So how multiple king, and another concept I told that it is not global, means localized means it is not global. So there is no contradiction between multiple kinking and localized deformation mechanism. Multiple kinking may occur. Suppose there is a 1 millimeter specimen, and in between 500 micron difference, two different kinking may occur to accommodate the rotation or compression state of sleep, where the sleep process is not properly activated or not feasible. It may occur, but that does not mean complete specimen are deforming by the kinking mechanism. In localized to area, that can be done. If you see like that, there is a two localized area where maybe kinking form, multiple king form, but all the kinking phenomena are localized. It does not mean that continuously all multiple, I did not tell that interconnected multiple kinking are going to form, which are all over the place. It is spread in a specimen. It's not my statement. My statement is very specific. Multiple kink may form, but they leads to a localized deformation process. Clear?
Yes, sir. Thank you, sir.
Okay. Now we are going to understand the twinning. What is the definition of twinning? If you want to define at a very textbook way, then one and more parts of a particular crystal regularly arranged and are in reverse position with reference to other parts or parts. Means the twin as the newly formed part as a twin crystal is a mirror image of its parent crystal. So twinned and untwinned parts of a crystal are mirror reflection of each other in certain plane of crystal. So in certain plane, that you can tell that mirror plane, and this mirror plane is also known as compositional plane. So a lattice, you can tell that. Now we can tell very conceptually that lattice is twin. When you say lattice is twin, when one or more parts atomic crystal structure is a regular arrangement of atom. So that part you have to remember. So regularly arranged are in reverse direction, reverse position with reference to its parent parts. That means twinned and untwinned parts of a particular crystal are really mirror image of each other and with reference to a certain plane of crystal. And this will be known as mirror plane, and this mirror plane also called compositional plane. And if you look at the picture, before twinning, what is happened, and after twinning, what is the structure, then the concept of your regarding the twinning as a definition or by definition, what actually feature on twinning should exhibit, that you can understand very easily. And the green line is actually twinning plane. You can tell the compositional plane or you can tell the mirror plane. Now we are going to understand glide versus twinning comparison. So it looks like a glide, but it's not glide. So in the comparison, first we will see in the perspective of atomic movement. So atoms move a whole number of atomic spacing on a single plane, that actually known as glide. But on the contrary, if you look at twinning process, planes of atoms move fractional atomic spacing. Fraction of what? Fraction of lattice and lattice parameter by atomic spacing and distributed over entire volume. So then you can tell this is a twinning. And what will be the microscopic appearance of the glide? Thin lines. But in case of twinning, wide bands or broad lines, certain lines will be broadened. And in the perspective of lattice orientation, no change in lattice orientation going to happen in case of glide. The steps are only visible on the surface of the crystal and can be removed by polishing. So after polishing, there is no evidence of slip. If you cut those steps through polishing technique, then you are not going to see any evidence, any history of the specimen having such glide phenomenon, glide activities. But in case of twinning, lattice orientation changes. Surface polishing will not destroy the evidence of twinning. So the evidence of twinning will be seen even you are going to finish the surface. After you're finishing the surface also, you can see the evidence of twinning. This is the basic fundamental differences. These are the fundamental differences between glide and twinning phenomena. So now if you look at this picture, it will tell much more detail about twinning phenomena. So in this figure, if you look at open circles, represent the position of atom before twinning. And the solid circles are going to represent the position of atoms just after twinning. After twinning, just is not important because after that you are not doing anything. You're just taking before twinning a one open circle based structure and after the twinning, the closed or filled circle based structure. The choice of compositional plane and the exact location of solid circles are crystal specific. You can understand that, and you can tell that is the mostly to the non-lattice location or non-lattice position. But it is certainly, or of course, it is not random. That you should remember. It is not random, but it is non-lattice location. So that one should not take a one should not mistake that non-lattice location and random things, random pattern are same. That is not going to be the same. So again, I am repeating, those solid circuits, exact location of solid circuit are going to have different crystal for different, going to be different for different crystal. Means it is a crystal specific phenomenon. And mostly or largely, those are non-lattice location or position. And you certainly remember that, or of course, you should remember that it is not random, but it is not random. So also you can see in the figure, stable twinning causes permanent deformation. That means new atomic arrangement is also stable. So you have to find the energy versus lattice parameter. You see the derivatives, then there should be a local minimum. So you should remember that it is also a mechanism of plastic deformation. Now we have to accept the significance of twinning. This twinning phenomena also a mechanism for plastic deformation, is also responsible for plastic deformation process. It's a well accepted mechanism for plastic deformation. Although if you look at its role is fairly limited as compared to dislocation glide. If you compare with the dislocation glide, its role is not so dominant over globally or for different grade, but it is one of the significant, but still it is one of the significant deformation mechanism in case of you are considering materials where dislocation glide is difficult. What kind of materials? Suppose HCP metals. cross-slip depressed metals, low stocking fault energy metals. Having cross-slip depressed, they are not going to have so much freely cross-slip mechanism going to operative. And BCC metals, which are not so much dislocation glide friendly materials or crystal structure. Or if you take certain deformation process at high strain rate, then also you are going to see the twin deformation mechanism. Where? Why? Where you are going to see, or when we are going to see, when the dislocation glide phenomena is not so easily operative. You should remember that. Now, if you look at the picture, atoms just above the twin plane move in a coordinated manner to produce shape change. Unlike slip, due to dislocation, where intermediate location of dislocation cause deformation. So it is not the same. There is a striking differences are there. So you should remember that and should pay attention on that. So therefore, or hence, theoretical stress for twinning is really very high because that is in absence of dislocation which may assist twinning. So in case of twinning, atoms move by less than one atomic spacing. This is different than what we see during dislocation slip. The movement of atoms is multiple of lattice parameter or atomic spacing. But in case of twinning, atomic movement is less than one atomic spacing. So distance also you can confirm by critically observing the picture presented in the slide. So distance moved by each atomic plane, you can see it's proportional to the distance from twin plane. If you look at also in the picture, and how can you get that kind of inference? That if movement of second plane from composition plane or mirror plane, whatever, if you take that alpha, then third plane will be 2 alpha and many more. So it actually tells you that distance moved by each atomic plane is invariably, or it is a proportional to the distance from the twin plane. So twin formation during deformation, people used to name that deformation twin, is very often understood to occur due to motion of edge dislocation, which are generally partial, and those edge dislocation same type. So twinning, however, require cooperative dislocation displacement. It is very important to understand. If you look at the picture, that then you can understand easily why tuning require cooperative dislocation displacement. In the first figure, let a partial dislocation go part way through and one underlying slip plane perpendicular to the slide. It changes stacking sequence. If you understand, then you can see that stacking sequence in the violet color. If you look at that highlighted area, and next stage, the first partial passes through, and the second partial is part way through on the next adjacent plane, and let third partial go part away through that. So if you look at it, it's very easy to understand. Okay. So now the stacking sequence are going to change due to such phenomena. Now we are going to understand what are the characteristics of twinning. So what are the characteristics? Twinning distributed over entire volume, not confined to a single plane. So it can be distributed to the entire volume, not going to be confined into a single plane. Twinning happens very quickly, speed of sound in case of material sometimes. So high strain rate, that's why it also sometimes leads to formation of twinning, or twinning mechanism going to be operative at such condition. as a plastic deformation mechanism. And cooperative motion of many planes of atom, with each plane moving only a small distance, then only you are going to see the twinning deformation or deformation twinning. So lattice is rotated, not distorted. One should remember very well. In case of twinning phenomena, lattice is rotated, not distorted. And there is not any possibility or no possibility for having phase transformation. We know what is phase, that physically distinct, chemically homogeneous, mechanically separable part of a system. Means phase, and which in case of metallic system, we used to identify physically distinct through crystal structure. So it's not going to having any change in phase due to having twinning phenomena. So there will be not at all phase transformation. Lattice just is rotated, not distorted. Those things one should remember. So rules of twinning, the fundamental rule. Crystal orientation is rotated, but crystal is not distorted. Again, I am repeating that. And the crystal structure is unchanged as a result of twinning. So basis vector maintain same mutual angle and length. Solving for the vector combination that follow the above rules yields the twinning system. So this is the rules of twinning. Now deformation and annealing twinning we have to understand. So deformation twinning already we have discussed. During the deformation is the twinning going to occur to accommodate the problem associated with sleep or gliding of dislocation glide, all those things. And annealing, twinning, heating and cooling during that time if thermal stress are created, and that going to have create a scenario where you get to see the fraction of atomic movement with respect to atomic spacing, then you are going to see the twin structure, that also known as annealing twinning. Okay. Now you have to understand the twin shape. So if you look at mechanical twin, the lenticular shape you are going to see. And in case of annealing twinning, the parallel sides twinning from one gain boundary to one gain boundary is revealed. So alpha angle will decrease in case of lenticular shape with the increasing shear strength. If you enhance the shear strength, then there is you are going to see the edge of lenticular shape much more steeper. So alpha will decrease. And generally, twin initiation space is much large. So we already know that there is a striking difference between twinning and dislocation glide. Slip occurs in atomic distances, while twinning occurs in a fraction of atomic distances. Stress required to cause a slip is much smaller than the stress required to continue it because of interaction with other dislocation leading to strain hardening. Whereas stress required to nucleate twinning is often higher than the stress required to propagate twinning. So nucleate the twin is need more stress with respect to propagating the twin. Stress required for the propagating the twin. But this is not the case, this is not the correct thing for dislocation glide. In case of dislocation glide, stress required to cause a slip is smaller compared to the stress required to continue that deformation, because we know or we are going to understand that strain hardening or work hardening, that dislocation interaction leading to strain hardening process. The orientation of plane does not change following slip on the planes, but they do due to tuning. But in case of tuning, the orientation plane can change or may change. Already we have discussed that. And twin markings can be distinguished from slip lines by repolishing the surface and etching. If it is a slip lines, then if you repolish in the surface, then it will go. But twinning lie marking not going to be eliminated. So thank you. That's all for discussing twinning phenomena. Any doubt?